So welcome everyone to this week's second CVAS lecture in the series From the Butterfly's Wings, so from the shortest timescales to the age of the Earth. And I'm really pleased to announce our second speaker, Christian Grams, who will speak about the subseasonal to seasonal climate variability with a focus on, let's say, Europe. And I would like to introduce our speaker briefly. Christian Grams studied meteorology at the Karlsruhe Institute of Technology. He then went on to also obtain a PhD in physics in Karlsruhe. He then moved to Switzerland, where at ETH he first was part of a research group on atmospheric dynamics as a postdoc, and later then won a rather prestigious Ambizione Swiss National Science Foundation grant to study climate, and in particular large-scale dynamics and variability. And this is really also the basis, I think, as it's my understanding, for your Helmholtz Young Investigator Group, which you started in Karlsruhe in 2017, and which you are leading since then. And I am quite curious and looking forward to hearing on your background, but also on the latest results from your research group. And with that, I don't want to talk more. Christian, the floor is yours. I'm looking forward to your presentation.
Yeah, good afternoon, everybody. And thank you, Kira, for the invitation and organizing this seminar series. Yeah, it's really a pleasure to be here and be part of this adventure across scales. So my part is now still remaining now in the weather scales, and I want to talk about the synoptic to subseasonal, rather weather variability with focus on the extratropics and Europe. And to kick that off, I want to show you, basically, I want to frame it into the weather forecast topic, because we have really a forecast challenge. When you are an end user and you want to know what the weather looks like, you might visit web pages like these and see then a weather chart for the next 2 weeks. And it gives you kind of security that around St. Nicolaus Day, it would be cold, and later there might be rainy and cool, but then also milder weather. But this is probably not the way you should do it, because if you look at professional forecasts that forecasters, for instance, at German Weather Service would look like, they would look like at a different field, not a temperature at the surface, but at higher levels, 850 hectopascal, we say. This is a pressure height, and it is roughly 1.5 kilometers above ground. And there you see that in the first days now, the first 3 days, there's quite security that it is, for this time of year, rather mild air mass. But then you get this huge spread of temperature remaining at that level, or it becomes rather cool at that level. And that means there is a lot of uncertainty evolving already after 3 days, or here in this case, but usually around after 6 days, such a local forecast for a point like Heidelberg, and predicting at the hour or at the day becomes quite uncertain. And this is basically due to the chaotic error growth and limited predictability of such local weather at a given location and a given time. And there you see that weather forecasting has the challenge that basically atmospheric phenomena are intrinsically coupled in temporal and spatial scales. When you look at this local weather, you look at individual clouds or a convective cell, and this goes on in the time scale of minutes to hours. And you learned a lot by Jörg Schmidtli a week ago about these really second, minute to hour scales ranging from meters to a few kilometers. And this is where weather starts. But when you go up scales, you come to a diurnal cycle in the land sea breezes, for instance, or then even lasting several days, a front of an extratropical cyclone. And then you enter actually the synoptic scales, which are basically in the spatial scale affecting an entire country or even a continent. And the weather systems like extratropical cyclones or anticyclone last usually several days. And then you gradually transition into what we call subseasonal time scales, where you look rather at hemispheric flow patterns, or patterns that affect entire Europe. So here, this is a weather situation where you have several cyclones, and it is basically on the mean characterized by the cyclone activity all across over the North Atlantic and Europe. And this is now the subseasonal timescale, which basically describes weather for several weeks, for several days to a few weeks. And if you go even higher in scales, you're still in weather, but now you're in the subseasonal to seasonal prediction, where hemispheric patterns, and in particular tropical convection, becomes a player. And there is, for instance, the so-called Metten-Julian oscillation. It is a 30 to 60 day oscillation of enhanced convection around the equator from the Indian into the Western North Pacific. But also on seasonal timescales, you have the El Nino Southern Oscillation phenomenon, which remains for several months and basically is also still a weather phenomenon, but on seasonal scales. And I will not talk about climate today, because here you will hear a lot by other experts, and there you look at the long-term climate mean, and this affects basically the state of the atmosphere on the entire globe. And when it comes to weather forecasting now, we basically have an initial condition problem for the classical weather forecast. So on short range from minutes to a few days, or also the medium range where it goes for several days to weeks, you heavily rely on an accurate state of your initial state, and then you solve physical equations and integrate them forward in time to yield this weather forecast. And the focus is here still on a local, like Heidelberg. And when it comes then to the longer time scales, long-range weather prediction for seasonal forecasting or climate projections, then you have a boundary condition problem. So you no longer rely on the initial conditions, but rather on the boundary conditions set, for instance, by the ocean states or by greenhouse gas concentrations or the insolation. And for seasonal forecasting, also the annual cycle of the sun. And the subseasonal forecasting now is just in between, and it's also called extended range. So it's in this gray zone of predicting the weather for several weeks to a few months, and it still relies on initial conditions. There is predictability in boundary conditions, but you have really a problem here, which is depicted in this schematic from a paper, because it basically simplifies the skill level that you have on these different ranges. On the weather forecast range of short to medium range, you usually, for a very short-term forecast, you have excellent skills. So we can predict what will be the weather in 1 hour from now. And this skill then rapidly drops up to a saturation. This is the chaotic error growth in the forecast from 10 days or 15 days. Then you lose the skill. Whereas on the long range, so for seasonal forecast, when you have predictability, for instance, from land surface conditions or ocean conditions, you have a decent skill for these seasonal forecasts where you look at seasonal or monthly averages. But in between, generally, the subseasonal forecasts have poor skill, where the initial conditions are already too bad represented. You have error growth here, but you cannot yet exploit the predictability on the longer range. And to illustrate that, this is now just a chaotic picture, but this is what subseasonal to seasonal prediction deals with. Basically, it looks at the scale interaction from weather and these initial condition problems and climate prediction. And you see, I want to focus now only on the extratropics. You see, for instance, in green here, the jet stream, which is a wavy pattern here in the extratropics, and a weather phenomenon that deals within that impacts subseasonal prediction, extratropical cyclones embedded in there, or blocking anticyclones. But on the longer time scales, you have this tropical convection from ENSO on seasonal time scales, or MGO on 30 to 60 day time scales. And there are these teleconnections which feed back to our weather in Europe. And basically, you have to make this right to get good subseasonal forecasts. And with that, I have already set the scene for this lecture or the seminar today. So basically, I want to address these topics, and I already have talked about the scales in weather forecasting. And I start with the first take-home message from this introductory chapter. So basically, what should be obvious is that in weather forecasting, but generally in atmospheric physics, temporal and spatial scales are always intrinsically coupled, in the sense that small temporal scales go along with small scale spatial scale phenomena, and so on. And the weather forecasting is in essence an initial condition problem where you rely on an accurate estimation of the current state of the atmosphere and integrate forward in time. Whereas in climate prediction, where you look more on the average state of the atmosphere, you have a boundary condition problem that relies on a good estimation of boundary conditions that drive the atmosphere, like the greenhouse gas concentrations and precession and inclination of the Earth's axis. Kira, something popped up, but there's nothing in the chat or something that no, everything is fine. Okay. Yeah, and then the subseasonal to seasonal prediction, which is abbreviated S2S prediction, is really at the interface of both and relies on both. And I now want to continue with focus on the extratropics on discussing what drives the variability on synoptic scales. So these are the weather scales of several days, like extratropical cyclone activity, and then also on subseasonal variability of a few weeks to a few months. And I will wrap up with key challenges in the subseasonal variability. So to approach the synoptic variability, I show you now a weather chart which looks at the North Pole, so from above on the Earth. So it's a stereographic projection, and it shows the wind speed at 200 hectopascals, which is 8 to 10 kilometers in height. And it's actually yesterday's situation. And when you look at that, the green shading shows you there are distinct regions where you have a so-called jet streak. So it's a local maximum of wind speed where wind speeds exceed 80 meters per second, so more than 200 kilometers per hour. And basically the jet stream is organized in this circum-global westerly flow. But you see at the same time that it is here over Asia now very zonally aligned. And then suddenly it splits into a branch which diverts towards Alaska and then becomes weaker. And a new branch in the subtropics emerge that go over Mexico and the US, and then split again in a heavily deflected poleward branch towards Greenland. And again, a southern branch, which then restarts in a subtropical jet stream, which is weakly undulated over Africa and Arabia, and then feeds into the jet stream. So basically, this is a typical situation of what happens with the jet stream. You have zonal flow situations, you have wavy flow situation, and you have something where we say a blocked situation where the westerly flow is highly diverted. And all this activity is basically governed by so-called extratropical Rossby waves. And to approach that, I now have prepared some schematics which explain you the physics behind Rossby waves without actually looking in the equations. So this is now a schematic of such a jet streak. You see again the highest wind speed in the center of this graph, and also depicted by this vector, so a strong westerly wind. And to the north and to the south, the wind speed becomes weaker. And when you now imagine you would have a paddle or an air parcel embedded here south or north of the jet streak, you will get a certain rotation of such a paddle, because here to the south of the jet streak, on the northern side, you have higher wind speeds than below, so you get a rotation within that wind field. And vice versa, on the northern side, such a paddle would rotate cyclonically, so against the clock. And you also get a rotation, but from opposite sign. And this rotation is, you can also depict in mathematics. So it's basically what we call a shear vorticity. So you have a sheared wind field. And that means that you get a negative vorticity to the south and a positive vorticity, which is simply the rotation. Mathematically, it's the rotation of the wind vector. To the north, you have positive values. And actually, in dynamic meteorology, we look at another quantity which unites that also with thermodynamics, and we call it then potential vorticity, but you only need to understand the basics for today. So I actually show here a weather chart, randomly chosen, and it depicts this field potential vorticity, but the vorticity field would look similar. And what you see now in blue shades are low values of this vorticity, and in yellow shades, very high values. And you have a very sharp gradient here over the Atlantic in that case. And this is also actually where you have the highest wind speeds along this gradient. And the wind speed is again here in the dashed contour shown, but also in the length of the wind vector. And you see this increase of wind speed up to a jet streak of up to 80 meters per second, and then a decrease again. So this should just show that you can also look at a jet stream in this metric of vorticity, and it aligns along a very sharp gradient. And this gradient now serves as a waveguide. On the next slide, my gray bar depicts basically this gradient and separates high potential vorticity air on the north from low potential vorticity to the south. And this vorticity now behaves in a way if you, for some reason, there are mechanisms which deflect this waveguide, and you get a deflection to the equator, so southward. That means you get high potential vorticity air in an environment where around it you have lower vorticity. And that depicts a positive anomaly in that region. And now vorticity behaves in a way that this triggers a wind field. And for positive values, it triggers a cyclonic counterclockwise wind field. And this is now not directly the shear that I showed before. You can simply imagine you have this cyclonic circulation around the anomaly. And I depict it here now with arrows, because what happens, there is also a far field effect. It happens that you have on the eastern flank, you have a southward wind component, on the western flank, a northward wind component. And this now advects your low potential vorticity air poleward and your high potential vorticity air in that region equatorward. So that at the next time step, your original anomaly propagated westward, but a new negative anomaly emerged at the leading edge, simply from this advection. And that means, again, now you have these induced wind fields that further propagate the original anomaly westward and produce new anomalies at the leading edge. And on the wave guide, you get now a wave pattern, basically, that emerges and propagates further. I want to show, so basically what we learned, we have a westward propagation relative to a base current. I didn't show that general jet yet. And you get a downstream development, downstream because the general flow goes to the east. So at the leading edge, you get new wave packets. But in reality, of course, you have this strong westerly jet so that the whole wave pattern is also advected. So that means the whole pattern further propagates eastward. And the original one with phase speed, which is slower than the actual jet because it, relative to the jet, it propagates westward. And at the leading edge, you have new wave packets emerging, which are actually faster than an air parcel. So if you're an air parcel, this wave would propagate away from you. But an air parcel would flow through the original wave. And I want to show you this now on a weather chart, actually, this evolution. Again, on a slightly different field, I show geopotential height, which is a measure for pressure at high elevations. But generally, where you have a dense gradient of these contours, this is also where the jet stream is. And I show that for simplicity, because in this situation, you now see over North America, you have a trough and a weak ridge in this initial state. And I go forward now 24-hourly, and you see how this wave pattern slowly moves further eastward. And there is a new ridge emerging, a new trough, and even over Europe is a new ridge forming, so that the entire flow becomes more wavy. But what you also see, the pattern becomes also more amplified. So it propagates and becomes amplified, and at some stage, the waves are so wide, so the wavelength is so big that in particular, this ridge 2, which I depict here, becomes stalled. So it becomes persistent over the Atlantic. And at the flanks, you see this tilting of the troughs. So the propagation, which I showed you before, is only half the story. You also get an amplification of the flow pattern. And this is because this near tropopause anomaly also has a far field effect to the surface. And when in the surface you have a frontal zone, this likewise induces basically a low pressure system near the surface. So you get a cold front and a warm front. The warm air penetrates poleward. And this depicts now a positive temperature anomaly near the ground, which likewise induces a wind field, which is depicted by the open arrow here. And this wind field also has a far field effect near the tropopause. but now you have a phase shift. So it means you get a northerly flow component right in the center of the original anomaly, and a southerly flow component of the downstream negative anomaly. And that means amplification, because now in the area of your trough, you further amplify the trough. And I depict it like that. So this is basically how such a Rossby wave pattern can further amplify. And I show this briefly now in this other depiction, the same weather situation, but now in a complicated chart, which again shows you this vorticity. So it's the same situation. You have the trough here, the ridge here, and the trough, the initial trough, but it is a bit more patchy, this pattern. But what I want to highlight here, in addition, we show the surface pressure, and there is already a low pressure system ahead of this trough too. And when I go forward in time, this low pressure system becomes deeper, along with the amplification of the ridge. So you have now a very strong low pressure system over Newfoundland. At some point this dissipates, but what remains is a high pressure system near the surface, which becomes stationary over the Atlantic. And at the upper levels, you have this highly deflected jet stream, which is co-aligned with the surface high pressure system. And that means this Rossby wave activity is intrinsically coupled also to surface weather systems like the extratropical cyclones and the high pressure systems and their evolution. And this is what is a key driver of synoptic variability, because these weather systems go along with all type of phenomena ranging from few hours when a front passes by to a few days when you have generally stormy conditions or high pressure situations. But at the same time, the key thing here is that you get this stationary state suddenly in the Rossby wave pattern. And that's when we enter now subseasonal timescales. So I briefly sum up the synoptic variability. For synoptic variability in the extratropics, the jet stream is a key ingredient because it kind of serves as a waveguide for upper tropospheric Rossby waves, which propagate and amplify along this waveguide and govern the synoptic weather variability, because they also trigger surface weather systems like extratropical cyclones and anticyclones. And yeah, these develop embedded in this Rossby wave activity. And now when we have suddenly a very highly amplified flow and stationary flow, that means the pattern doesn't change for several days to even a few weeks or a month. And this is now when we enter the subseasonal time scales and spatial scales. And in the extratropics, a depiction of this, it can be, basically these stationary states are reflected in so-called weather regimes. And they are defined as quasi-stationary, persistent, and recurrent large-scale flow patterns. And I said already, they describe the multi-day variability of the large-scale flow and the associated surface weather over a specific region. And for Europe, the simplest depiction, you can go bimodal. And there is a range of regimes which are characterized by low pressure activity, often close to Iceland. And that brings more mild and windy and rainy weather into Europe, which lasts usually for 1 or 2 weeks then. On the other hand, you have blocked regimes, like at the moment, where you have a high pressure system sitting somewhere over Europe, and that often brings you calm conditions while extratropical cyclones remain outside on the Atlantic. Or in winter, fog. I don't know, today it was sunny in Karlsruhe. I'm not sure whether in Heidelberg you were lucky as well. Yesterday it was very gray here. But this is what you have to deal with in terms of surface weather during blocked situations, and that lasts for several days, as you know, in winter. And it can become depressing then. But this is basically the subseasonal variability. And I want to elaborate on that now with a new definition that we use for 7 regimes. I skipped the technical details. I directly show these patterns. We also have the group of cyclonic regimes, but we have 3 variants of that. So we have what we call the Atlantic trough regime with negative pressure or geopotential height anomalies close to the UK, and that brings low pressure systems close to Western and Central Europe. And then you have the zonal regime with the cyclonic activity more focused to the Greenland Icelandic region. And we have a Scandinavian trough regime where cyclone low pressure anomalies are more focused towards Scandinavia and the Nordic seas. And on the other hand, we have high pressure situations where the core of the high pressure system is in different regions. We have an Atlantic ridge regime with the ridge off the coasts of Europe. And we have European blocking where the ridge is more over Western Europe and Central Europe, and the anomaly centered over the North Sea. And we have a Scandinavian blocking where high pressure is more situated over Scandinavia and Eastern Europe, and Greenland blocking where we have the high pressure situated over Greenland. So these are basically what emerges from a 40-year data set analysis, which are the most frequent different regimes, and they occur year-round. So this is now the regime frequency for these different regimes. The reddish colors are cyclonic regime, and yellow, green, bluish are blocked regimes. And you see in winter, we have a tendency to have more of the cyclonic regimes than in summer, and vice versa, more of the blocked regimes in summer than in winter. And roughly about 1/3 or 30% of all days cannot be characterized by these most typical patterns. They are unusual situations or transitions between these regimes. But why should we care about the regimes? And it is because basically they modulate weather or surface climate variability on these subseasonal timescales. So they characterize the weather for several days to a few weeks. And you can see that in terms of wind power variability on these timescales, or the modulation of the likelihood of heavy precipitation and moisture transport into Europe. You can see that in changes of likelihood of heat waves in summer or cold spells in winter. And what I want to elaborate today still is on the wind power variability. And for that, I show you basically the winter 100-meter wind anomaly over Europe in these different regimes on average. So if you first only look at the color shading, which shows a positive wind speed anomaly in reddish colors, and bluish colors a reduced wind speed. And you see that a bit like expected during regimes which are characterized by low pressure activity, you have enhanced wind speeds either at the Western European coast in the North Sea, or more on the North Sea and Northern Europe region, or again over wide parts of Western and also Eastern Europe. In contrast, during these blocked regimes, you have reduced wind speeds due to the high pressure situation, and the center of these reduced wind speeds changes according to the blocked regime that you're looking at. But it is striking, for instance, the zonal and European blocking regimes have quite antisymmetric patterns. While in the zonal regime, you have enhanced wind speed in the North Sea region, you have reduced wind speeds during the European blocking regime. And how this translates now to wind power output, we simulated basically with considering the national capacities of wind power as in 2015. These are depicted here in numbers, and then we looked at the relative change of wind power output compared to the winter mean. And we show this for each country in a graph like that, where we show each bar, which is the relative change in the respective regime. And as you might expect, during cyclonic regimes over all of Europe, we have a surplus of around 20% compared to the winter mean of wind power output, whereas in blocked regimes, we have a reduction up to 20%. But if you zoom down on the country scale, you see that exaggerates, because in Germany, we get a surplus in this orange regime of up to 50% more than the winter mean, whereas in the European blocking, you even get a reduction of 60% compared to the winter mean. So there's a high variability between these regimes, which typically last a week or 2 weeks. And generally, all countries here around the North and Baltic Seas have this behavior, with this antisymmetric behavior between cyclonic and blocked regimes. But if you look at other countries like Iberia, they behave quite differently, with some surplus of wind power output in blocked regimes. And interestingly, also the Balkans has generally a surplus during blocked regimes. And we computed now, but we computed now what this means actually for the Europe-wide output during weather situations. And this chart now shows you first in this olive color where we currently have installed wind power capacity. And you see currently in Iberia, there's a lot of wind power. This is the second most installed capacity. The most capacity is in Germany and UK. And all the colored blue and red crosses show where there are planned wind parks. And you see this is highly focused now in this region of the North and Baltic seas, where we also have this contrasting behavior weather-wise. We now computed for all of Europe, what would it mean if we have a weather situation, which happens quite some time, that you change from this blocked situation depicted in green into a cyclonic situation and back. And this is now exemplarily the weather conditions in December 1992 and January 1993. And it shows you the Europe-wide wind power output with a hypothetical wind park of 2015. During the Greenland blocking, you start at rather low levels of roughly 20 gigawatts, and this then gradually ramps up to 50 gigawatts. And then you have a sudden drop when you have a regime transition back in this blocked state. And when you now do what we actually do, we double the capacity in Europe, and we put everything in the North Sea and into the Baltic Sea. This is what will happen in such a weather situation. Overall, you have a higher power output also during the blocked situation, but this then basically amplifies much more. You get during the windy situation, you have 150 gigawatts of power output, but then a sudden drop back when the regime transition occurs to 50 gigawatts. And this drop is 100 gigawatts. So that means you switch off 100 nuclear power plants at once within a few hours when this regime transition happens. And this is, of course, something that the system will not cover, basically. And it means that you will not harvest this peak probably. But what is important now, if you reflect the wind patterns, and you know that basically during blocked situation, you have more wind in the Balkans and Iberia, but also in northern Scandinavia, we played around and deployed this capacity not in the North Sea, where we already have a lot of wind capacity, but in these peripheral regions. Then you can see that you can balance basically the power output. You get the same mean winter output, but at a much lower level of variability. So from that study, we concluded that this multi-day variability, which is imposed by weather regimes, or multi-week, I forgot to say that this windy spell lasted here 3 weeks, and also the blocked regime lasted for 2 weeks. So this multi-day variability in wind power output could be balanced if you considered these wind patterns that go along with weather regimes, with your deployment. Okay, and the second topic I only want to talk about with this overview slide is also an important topic, which is about heavy precipitation. And here in the master thesis, we looked at how the moisture flux into Europe in terms of so-called atmospheric rivers changes in the different regimes. So the small maps here show the entire Atlantic and Europe. So Europe is in that corner. But what you basically see is that depending in which regime you are, you have a different frequency of this phenomena, which we call atmospheric river, and which are major moisture supply to Europe. And along with this moisture supply, you also change the likelihood of heavy precipitation events, which is shown here in this patchy blue colors. This is now a zoom on Europe. And you see that depending on which regime you get, sometimes you triple the likelihood of having really extreme precipitation in that situation. And often it's associated with atmospheric rivers. Unfortunately, I don't have time to go into more details here. I want to repeat that weather regimes also affect surface weather in terms of heat waves and cold air outbreaks. And I now wrap up this third chapter. So this in the extra topics, this subseasonal variability is generally governed by these persistent states, which you can describe in weather regimes. And they are important for also the weather variability and extreme weather, that the change in likelihood for extreme weather. And the last 2 or 3 minutes, I want to give a bit an outlook on the key challenges in subseasonal prediction. I outlined, again, it is the scale interaction, but I want to depict this a bit more quantitatively here in this study. we show forecast skill. This is a skill metric for Europe, the anomaly correlation, and usually a good or a useful forecast would have a skill above 50 to 60% in that metric. And you see that this metric drops below that critical level already after 10 days. But this drop depends on in which regime state you start a forecast. And you gain in some regimes a few days of predictability. So I want to stress here that there are opportunities that depending on which regime you are, you might have a longer range of a good forecast. On the other hand, we also know that for a 6-day forecast, this is now the same metric, but shown for different forecast initialization times. That means we look here different days, how good the 6-day forecast was, and usually you have a decent skill level. But then there are episodes where you have such dropouts, where you do not have skill in the 6-day forecast. And here, in this particular case, we looked into more detail, and there are also systematic studies. They happen frequently, and they are often related to regime transitions or the setup of a blocking anticyclone. The forecast just doesn't get right how the block establishes. And this is now a real problem if it's so early in still the medium range forecast, because the world leading center for weather forecast is the European Center for Medium Range Weather Forecast, but they aim to predict actually regime transitions up to 4 weeks ahead. They put the aim on 2025, and it's still a way to go. And likewise, you can look in a different metric here, more close to the weather systems. This graph here now shows the frequency bias in different models, subseasonal forecast models for a week 2 forecast. So how well does the model represent blocking in a longitudinal band over the extratropics in this second forecast week? And you see that literally all models have a problem over Europe. They have too little blocking. And here our postdoc in the group, Julian Quinting, showed that this is actually related to this Rossby wave propagation, that these Rossby waves do not break over Europe, but propagate too far inland. And the potential mechanism I didn't talk about today, or no, we are sure it is a mechanism that plays a role here, basically unites now the scales really from the cloud microphysics going on second and meter scales up to the subseasonal scale, because it is when you have this coupling of the lower and upper level flow, what also happens in these cyclones is that you have ascending air streams. And when you have ascending moist, warm air, condensation sets in. The condensation gives you latent heat release, which further enhances the ascending motion. And basically what you do by forming precipitation in the warm sector of extratropical cyclones, you also transport an air mass in the upper troposphere, which further inflates such blocking anticyclones downstream. And in other studies with colleagues at ETH Zurich, we showed that actually 50% of the air mass in these highly amplified blocking ridges has a relation to such latent heat release. So this is a major problem in forecasting. If you get the process wrong, you will not get the Rossby wave pattern and even the subseasonal timescales right. And this is actually also the challenge, but there lies also the opportunity, because the forecast opportunity really lies in these lower climate modes like the MGO or ENSO, but also the stratospheric polar vortex, which as themselves have a predictability of on timescales from 30 to 90 days, but often this gets diluted due to these weather processes. So the key question is, how can we actually exploit these sources of predictability in subseasonal forecasts for the extratropics? And this is what my group is looking at. We approach this problem from the weather's case, because we want to particularly understand this outflow from latent heat release, how this affects the weather regime life cycle. So we study the large-scale circulation in terms of weather regimes, and try to understand the processes behind that and how weather regimes affect surface weather in extremes. And we think by better representing the weather regimes in numerical models, we can improve forecasts. And therefore we work closely with the German Weather Service and ECMWF and also a WMO, World Meteorological Organization initiative on subseasonal prediction. If you want to learn more, visit our webpage. And with that, I come to the summary slide. So my aim was that you get a sense of the coupling of the scales in atmospheric phenomena. And the take-home message is that the weather forecasting is really an initial condition problem, which relies on good initial conditions to integrate forward physical equations, whereas climate projections are a boundary condition problem where you need to know the forcings of the Earth atmosphere rather than the exact initial states. And variability on synoptic scales is governed by the upper level jet and Rossby waves and weather systems that evolve along this waveguide. And the weather regimes can be used to describe this flow variability on subseasonal scales of several weeks. But it's a big challenge to accurately represent them currently. We have always these dropouts in forecasts, but there's hope because we can predict actually the slower modes on these scales like the MGO or the stratosphere. And with that, thank you. And I'm looking forward to the discussion.